All right, so who can give me an answer to exercise number 1, methane versus heptane? Leia. Okay, yeah. When we are talking about things that are structurally the same, we're just talking about a 1 carbon versus a 7 carbon chain. There's no functional groups. The higher molar mass is going to have the higher boiling point, okay? Why does having a higher molar mass or having a bigger chain give you a higher boiling point? Yeah. Yes, more dispersion forces. So higher probability if I've got just one carbon versus 7 carbons. Assume the hydrogen's attached to all of these. Then there's a greater probability that I will have a temporary dipole caused by the movement of electrons around this heptane molecule than around the methane molecule. I've got more bonds, more potential electrons total to move around, and so that's going to give me stronger dispersion forces, higher probability of a temporary dipole, higher probability of a stronger temporary dipole, higher probability that that's going to last a little bit longer and be able to affect molecules next to it, so it's going to be more likely to stick together. Yes? They would want you to talk about either dispersion or van der Waals forces. Those are sort of interchangeable to say that it's the larger molecule is going to have stronger dispersion forces, and that's going to increase the boiling point. Not in this case, because there are none. The temporary. I think if you just say dispersion forces, what I've seen so far, thinking about it in the MARC schemes, I think you just have to. They have to know that these have dispersion forces only, and that it's the stronger intermolecular forces that are going to give the higher boiling point. All right. So what about number 2, pentane versus 2-methylbutane? Somebody besides Leia, although I'm sure she has the right answer. Yeah, Natalie. Okay, it has a longer carbon chain. The molar mass is going to be exactly the same between these two because they are structural isomers. So the pentane is going to have a straight chain of 5 carbons. The 2-methylbutane is also going to have 5 carbons and the associated number of hydrogens. But it is going to be branched. Why does the straight chain have a higher boiling point? Jacob. Right, so if we have temporary dipoles here, it's going to be over a smaller spatial span, and so it's less likely that we're going to have electrons trapped on one end, and if that happens, that temporary dipole happens, it's going to be less distributed. It'll be less unevenly distributed across the whole of the molecule. So the more spherical the molecule is, the less dispersion force you're going to see, and the lower the boiling point. So this one is going to have a higher boiling point. The straight chain pentane is going to have a higher boiling point because those dispersion forces are going to be stronger. Now, if we had the difference between like an ethane, like 2 carbons, versus the branched butane here, obviously that would throw another kink into the mix. They're not going to ask you to say distinguish between the 2-methylbutane and the heptane because they're different in multiple ways. They're different in branching and they're different in molar mass. And so they're not going to ask you to determine which one wins out. Okay, so generally speaking, if they're going to ask you to make comparisons, it's going to be between 2 molecules that only have one of these things that is different between them. So either it's going to be a bigger molecule, or it's going to have to be the same size or roughly the same size but more branches. Or we're going to have something like number 3. So ethanol and propane. Okay, so anybody want to come up and draw ethanol and propane up on the board? Braden, come on up. Okay. That's correct. All right, so Braden's rocking the skeletal structure here. We've got carbon, carbon, and then the OH with the hydrogens assumed here. And here we've got 3 carbons with no oxygens, no hydroxyl group, okay? I'm just writing that in because I'm not sure everybody has the grasp of the skeletal structure. We haven't been using it much. I've been drawing it like this as opposed to the skeleton. I should probably switch to that. But this is essentially, they have almost exactly the same molar mass, all right? So who is going to have the higher boiling point? Yes. Why? Because of the oxygen. Nick, what about the oxygen gives us a higher boiling point? It's hydrogen bonding. It's the oxygen and hydrogen together, right? That bond between the oxygen and the hydrogen is very polar. The oxygen is very partially negative. The hydrogen is very partially positive. That's going to create the strongest permanent dipole that we can get, other than a hydrogen and fluorine. I mean, it's among the 3. Remember, hydrogen bonding is hydrogen directly bonded to oxygen, nitrogen, or fluorine. All of those 3 are going to be especially polar, and that's going to give it a pretty strong intermolecular force. Yes. Yes, hydroxyl group, yes. Yeah, so anytime you have the difference between an alkane and an alcohol, the alcohol is going to have the higher boiling point because of the potential for hydrogen bonding. And if you look, I meant to put this in a slide, but I did not. If you look on the previous page in your study guide, it gives a nice ranking of the boiling points of different functional groups. All right, and so at the bottom we have alkanes because those are completely nonpolar. There's nothing, there's a very slight polarity between carbon and hydrogen, but not enough to create anything more than dispersion forces. The next 3 you see have the carbonyl group, the carbon-oxygen double bond in various formats, the esters, the aldehydes, and the ketones. So those are going to have a polar bond, but not hydrogen bonding. Okay, so these next 3 are gonna have dipole-dipole interactions to varying degrees depending on how big they are and how many of those carbon-oxygen double bonds exist in the molecule. So something like acetone, for example, it is a liquid at room temperature, partially because of that carbon-oxygen double bond and the polarity that it produces. However, it's more volatile than an alcohol because it doesn't have hydrogen bonding. So if we compare something like acetone to an alcohol, the acetone is going to evaporate first. It's going to have a lower boiling point than the alcohol. All right. The top 3 alcohols, the carboxylic acids, and the amides, all have hydrogen bonding, either oxygen and hydrogen bonded directly together or nitrogen and hydrogen bonded directly together. So those are the ones that are going to have the highest boiling points out of our functional groups. Okay. So just keep either memorize this or think about the structures and why the alkanes versus the carbonyl groups versus the ones capable of hydrogen bonding would have different boiling points. Yes. Because because the O is what's bonded to the carbon. Yeah. So for example, if I was writing an alcohol on the end of this carbon, I would write it as HO, okay? Because the oxygen is what's bonded to the carbon. And over here, I'm going to write it as OH because, again, the oxygen and the carbon are what are bonded together. That's a good question. Thanks for asking that. Yes. Volatility? Mm-hmm. Yeah, so volatility is how, sorry. The volatility is how easy it is to evaporate. So if something is volatile, then it evaporates easily. So things like perfumes are volatile on purpose because they want it to be able to evaporate off your skin into the air around you and allow people to smell it, right? A lot of aromatic compounds that are, that create things that smell good have relatively high volatility, or that smell bad, right? And because they can travel, they easily vaporize and travel through the air. So if you have high volatility, you also have a low boiling point. It doesn't take much energy to get them to go into the gas phase. So boiling is generally considered like deliberate transition from liquid to gas by adding heat. All right, evaporation is spontaneous transition from liquid to gas in the absence of added heat. So volatility is how much evaporation is going to happen, usually at standard conditions. Okay. Good question. Okay. All right, so that's our boiling points. And so again, you won't be asked like the difference between ethanol and heptane, because those are different both in a significant difference in the size of the molecule as well as the functional group. It'll be like rank these similar sized molecules with different functional groups, or rank these alkanes of different sizes, or these alcohols of different sizes, or something like that, or these structural isomers. Okay. All right, moving on to more reactions. Sorry, I should have put the page number on here. We're down a fair bit here. We talked about the alkanes, and we talked about the addition reactions for the alkenes, the hydrogenation, the halogenation, and the hydration. So yes, so now we're on, thank you, page 32. So this is where we get into polymerization, and probably not going to have time to do this week, but at some point after the test, I will probably try to do the demo where you make nylon. Or the lab where you get to make nylon. It's actually pretty fun. You can make like a really long polymer chain if you do it right. So polymers are just poly, meaning many, mers. So a monomer is one unit of a polymer. Okay, a polymer is multiple units of a substance, and polymerization often happens when we have addition reactions between alkenes. So polyethylene is going to be multiple ethene molecules. What's going to happen is the double bonds are going to break, and we're going to end up with between each monomer, we're going to have single bonds to the next two carbon monomer over. Okay, so the way this is generally shown, you might be asked to draw, if there are say there are three monomers, what would the chain look like? And so you would draw three of these in a row. They might ask you just to draw the polymer of this addition reaction. So generally speaking, kind of like we do with the structural formulas, where you put it, if it's a repeating unit, you put it in parentheses with a subscript. But for polymers, the subscript is N, because it really depends on how long the reaction went, and whether it was broken up beforehand, and you'll get to see that. So it's the unit in parentheses with an N subscript saying some number of these strung together. Make sure that you get rid of the double bond when you're drawing that, because that's the thing that's going to be broken to make the bonds to the next unit. So, so that's the easiest basic one, and then there are several more in your study guide and in the chapter. PVC is essentially the same thing, but instead of an ethene molecule, we have chloroethene. So each ethene has has been substituted with one chlorine. Yes. Yeah. And so in this case, what we end up with is exactly the same thing, except there's a chlorine in each monomer. All right, so same thing, just make sure that the double bond is broken and you have whatever substituent is on there, and that the subscript is N. So there's an exercise here. It says draw the structure of the polymer made from 3 2-methylpropene monomer units. So let's start out with who can come up and draw 2-methylpropene as the monomer. Jacob, come on up. Okay. You're missing a hydrogen. Out there. Yep. Okay, great. All right, so we've got a propene, which means we've got a 3-carbon chain with a double bond. Now, it doesn't specify where that double bond is, but it doesn't matter because either way, it's going to be between carbon 1 and carbon 2. Because even if we do it, you know, if the double bond was over here, we would just number it in the opposite direction. Okay, so with propene, it's the same, unless it said that there were 2 double bonds. Okay, which you generally aren't going to see 2 double bonds next to each other like that. So. So we've got the double bond, and then it's 2-methyl. So on the second carbon, which again, it doesn't matter which way we count it, on the second carbon, we have a methyl group, okay? You can also think of this as, you can also draw it like this, which might make things a little bit easier. So a lot of times, if you think about the actual structure, the actual shape of the carbons that are involved in a double bond, it's going to be trigonal planar. So we're going to have this hydrogen, and then this carbon is going to have basically 2 methyl groups. Okay. So each of these is going to sort of have a trigonal planar structure. That, looking at it this way might make it a little bit easier to draw the polymer. Okay. So go ahead and draw a polymer with 3 units of this substance. So that's the monomer. Now draw the polymer made from 3 of those monomers. Yes. Yeah. So this is basically, this is the monomer unit. Okay. and then you can put it together as like a infinite chain, not infinite, but any length of the chain of this, and then this one, and then another one, and then another one, and then another one. This is the monomer unit, and so the N means it can be any number of those stuck together.
Oh, and so then we're making a polymer of this?
Uh-huh.
Is that, okay. So
Yep.
we have to turn it into a polymer and then.
Yep.
Okay.
Yeah.
So is this something like this? Just put two of them together?
Not exactly. So I suggest, again, looking at the way that I drew it. The way that Jacob drew it is correct, but the way that I drew it is going to make it a little easier to make your polymer. Yeah. Right, because it's going to have another something else on the end. It's either going to be a hydrogen there, or it's going to be another unit of the
So if it's
monomer.
just three, should I just put
Yeah.
hydrogen there?
Well, you can leave it like that. That's fine. 3. Yeah. Okay. All right, so what's going to happen here when we make it into a polymer is we're going to break that double bond and we're going to be connecting each of these together, right? So that the unit is going to be, the monomer is going to be this with the double bond broken and a bond on either side of the carbons, right? And so it's going to be this, however many of this. So if we're talking about 3 of these, then we've got 1, 2, 3. And you can either put hydrogens on their end or just leave it as, undetermined what those outside carbons are going to be attached to. But what's important is to note that it's the double bonded carbons that are going to be stuck to each other. All right, it's not the CH3 molecule out here that's going to be added on. It's going to be, so we're going to have so if we're adding 2 of these together, what we're going to do is we're going to break the double bond for each of these and form a single bond between the 2 carbons and then single bonds on each side. Yes? Right, this would be like the polymer in general, and if it asks you to draw 3 of them, then what it's asking you to do, if they ask you to draw a polymer with 3 units, they want to see the units next to each other so they know that you know which carbon goes on which carbon. Okay? If they just ask for the polymer unit, then, or the monomer unit or whatever, then you can draw it like this. So the answer is what's on the bottom. What's on the top is sort of the general polymer that will be formed with this substance. Okay? And so they can give you anything. They can put chlorines here, they can put methyl groups, they can put bromines, whatever. It's still going to be the same basic idea. The polymerization is still going to be the double bonded carbons losing the double bond and attaching to each other. Okay? Any questions on that? All right, now we get into the alcohols. So we've been sort of waltzing through by reactions of different functional groups. We started with the alkanes, then we did the alkenes. Now we're going to talk about alcohols. Alcohols can also undergo combustion. So I believe that you only need to know the formula for complete combustion. In Mike Jones's PowerPoints, he includes complete and incomplete, but I think that for alcohols, you only have to know complete combustion, unlike the alkanes. But regardless, it's the same idea, right? So we're taking the alcohol, we're reacting it with oxygen, we're making carbon dioxide and water. If it was incomplete combustion, you would be making either carbon monoxide, with less oxygen, or you would be making carbon with even, excuse me, with even less oxygen. So the only difference here is that, excuse me, when you are balancing the equation, you have to take all of the oxygens into account on the reactant side as well as the product side. So it just makes the balancing of the equation a little bit more complicated. So just notice that if you're asked to do something like that. You already have to do that on the product side with the CO2 and the H2O. So make sure when you're balancing these equations, this is why combustion reactions are a little bit tough. There is a formula. I'll see if I can find a good site that talks about the formula for complete combustion and post it for the balancing. But I just find it easier to do the balancing by hand. But I'll try to find that formula and post it for you. Okay, so we can combust alcohols. That's the easy part. It's just like combustion of the alkanes. The other type of reaction that you need to know about for the alcohols is what's called oxidation reactions. And this is, yeah, sorry. I don't, that's a good question. I don't have a good answer for it. So are the alkanes. So what makes it more flammable than other things? I mean, acetone's flammable too. Like, most organic compounds are flammable. All right, so that's why most of them are locked in the flammables cabinet. The alcohols, the ketones, and the halogenoalkanes are all in flammable cabinets. As far as what makes something more flammable than something else, that is a question that I don't have an answer to. It's a good one. I'm going to write that on the board for unanswered questions. All right. So the oxidation reactions, this is a little bit tricky to explain because we kind of skipped over the redox topic, which is topic 9. So talking about oxidation and reduction, it's going to make it a little harder to understand what's going on here. So let me just quickly say, oops, let's get out of that nasty orange color. The mnemonic for understanding what oxidation and reduction are is oil rig. So oxidation is loss, reduction is gain. And we're talking about electrons. Okay? So, so when something is oxidized, it has lost electrons. It has not exactly a higher charge, although that's sometimes the case, but it can be just a higher oxidation state within a molecule. Which I unfortunately don't have time to go into. But it basically means that that particular atom in the substance has lost an electron, and reduction involves gaining an electron. So oxidation reduction reactions, or redox reactions, is basically the movement of electrons from one thing to another, which is why it's the basis of electrochemistry, of the formation of batteries, of electrolysis, because what we're doing in a battery is moving electrons from one thing to another, and thus creating a current. Okay, so anything that is losing electrons is going to be oxidized. Anything that's gaining electrons is going to be reduced. Now, why it was originally called oxidation? Because it was often associated with gain of oxygen. Now, that is just a subset of oxidations, and reduction was often associated with gain of hydrogen. But it's more important to think about in terms of losing and gaining electrons, okay? And this is also, redox reactions are what happens in the electron transport chain in photosynthesis and in cellular respiration, the things that are going on in the membrane of the mitochondrion or in the membrane of the chloroplast. So that movement of electrons is what fuels your cells. That's where most of the ATP comes from. Okay. So when we talk about oxidation of an alcohol, what generally is happening is that the carbon-oxygen bond becomes, that this carbon is basically going to lose a hydrogen and form a double bond with the oxygen to make a carbonyl group, okay? And that's going to give us the primary alcohols. When the alcohol is on the end, it's going to give us an aldehyde. Yes? Yeah, okay. Why does this happen, and under what conditions does this happen? It requires an oxidizing agent. One of the usual ones is dichromate. In this case, our chromium changes from the dichromate into, that separates out and becomes the chromium 3+. So what's happening is this is, let me think about this. This is going to be 7 times -2, which is -14. It's going to be -16. And this is going to, so each of these CRs is going to have an oxidation state of +8. And it's going down to an oxidation state of +3. So the chromium is being reduced. It's gaining the electrons that are being taken out of the alcohol. Okay, and so that is why you need something like dichromate or permanganate or manganate solutions in order to make this happen. So it's the transfer of electrons away from the alcohol and to the catalyst. Yeah. The metal is being reduced while the alcohol is being oxidized. Redox reactions always have both things happening. If the electrons are being transferred, one substance is being oxidized, the other one is being reduced. Otherwise, you don't have a redox reaction. Yes, it's going from +8 to +3. Because it's gaining, each chromium is gaining 5 electrons in this state. Yeah. Yeah. Actually, wait, sorry, it's not going from +8. I did this wrong. This is +12. It's going from +6. No, that makes much more sense because then it's 6 electrons. I did that, sorry, it's been a long time. I did that wrong. But in any case, it's going from +6 to +3. And so it's each chromium is gaining 6 electrons in this process, and those electrons are coming from the alcohols, which is being oxidized. Nick, you had a question? Because the carbon can only make 4 bonds. Grace? Have 2 lone pairs also. Yeah. Okay. We'll come back to this about primary, secondary, and tertiary alcohols. But we are almost done with these reactions. And then we'll go on to talk a little bit about spectroscopy.